Okay, so welcome to Lab 5 practical illustration for Module 5 of Computational Chemistry for Experimentalists. Today we're going to talk about how to compute transition states and reaction rates. Now I've logged in remotely to one of the GigaLab computers and I've set up Gaussian running in the command line by setting the following environment variable, making sure that we know where the executable directory is. And I've got Gauss View Viewer up and running so that I can generate input files and look at output files. Now the first thing we're going to do, for this illustration, we're going to look at a simple gas phase tautomerization of thioacetic acid where the proton moves from the oxygen to the sulfur. In the lab report, you're going to look at a different reaction, the gas phase keto to enol tautomerization of a simple aldehyde. So we're going to start out by building our reactant geometry. We're going to end up doing 3 calculations, one on the reactant, one on the product, and then use those as inputs for one on the transition state. So we're going to start by creating a new molecule. The most important thing about doing these calculations in Gaussian is to remember that the order of the atoms matters. This is the only place where the order of the atoms matters. So if a carbon atom is atom number 1 in one geometry and it's atom number 2 in a second geometry, you're not going to be able to use those 2 geometries to find a transition state. And I'm going to show you exactly what I mean. So when you do these calculations, I strongly recommend that you follow exactly the procedure that we're going to follow here. So our first step is going to be to build our reactant, as I said. So I'm going to go up to the R group fragments, and I'm going to select a carboxy fragment. I'm going to put a methyl group so that we get an acetic acid. And I'm going to replace the C double bond O with C double bond S. This is thioacetic acid in the OH protonated tautomer. To make sure I know what's going on, I'm going to view the atom labels. So now carbon is atom number 1, oxygen is atom number 2, sulfur is number 8, hydrogen is number 3. Okay, undo that. Change all these window sizes so that I can actually look at one window at a time. Zoom in, and now I'm going to compute the ground state equilibrium geometry of this tautomer. So I'm going to set up a Gaussian calculation. It's going to be an optimization. Note here I'm going to optimize to a minimum. That's the default that we've been doing all along. I'm going to retain this, and I'm going to call this input file, save it as OH tautomer. Right now I'm saving everything in my documents folder, and I would move everything out of that at the end. Now I've saved that input file. I can go here into my terminal, check that I have ohtautomer.gjf, and I'm going to run. Run that calculation and generate the corresponding log file. This will take 30 seconds to a minute. Once I'm done, I'm going to open the output file in Gauss View, and then I'm going to use the optimized reactant geometry to generate my initial guess for the optimized product geometry. So I'm going to close this input file, and now I'm going to open, if I can, the output file, ohtautomer.log. And Gauss view doesn't work for reasons today, so what we're going to do is we're going to do C, G16W, form check, right? We're going to format the checkpoint file. Now we're going to go into Gauss view and open the formatted checkpoint file. That's our optimized geometry. I'm going to view the atom labels. Now, in order for this to work, I have to make sure that atom number 2 stays the oxygen atom, atom number 8 stays the sulfur atom, and atom number 3 stays the hydrogen atom. So I'm going to move atom number 3 over to the sulfur. Now, I'm going to do this using Gauss View's modify bond tools. Remember, we talked about before, these little sticks that are drawn between the atoms are not bonds. They don't come from electronic structure theory. They don't have any physical meaning except for this step where we treat the little sticks as springs between the atoms, where we use Gauss View's internal ball and spring molecular mechanics software to get initial guesses at geometries. So what I'm going to do, I'm going to use the modify bond tool to draw a little stick between atom 3 and atom 8. It's a little stick. I'm going to use the modify bond tool to remove the little stick between atom 3 and atom 2. I'm going to use the modify bond tool to draw 2 sticks, not 1 stick, between atoms 2 and atoms 1. And I'm not going to worry about the quote-unquote bond between the sulfur and the carbon. I'm not going to worry about it all. Now I'm going to go up here and I'm going to hit the little broom tool that says clean, and that's going to generate an initial guess geometry of the product. Now I'm going to set up a new Gaussian calculation. That's another optimization using our default method. I'm going to save this file. I have to click on the window, and I'm going to save this file as shtautomer.gjf. Now I go to my terminal window. I check I do have an shtautomer.gjf saved here. I'm going to run the calculation that's given by this input file. It'll take a little while to run the calculation, but it should get there. Once it's done, I'm going to format the checkpoint file that I generated, and I'm going to open that formatted checkpoint file in Gauss View and take a look to see if the optimized geometry makes sense. Does it look chemically reasonable? Format my checkpoint file, close this so I don't get confused, go in Gauss View and open shtautomer formatted checkpoint file. Okay, there we go. So now I have 2 calculations one for the OH protonated reactant and one for the S protonated product. One where the hydrogen is on the oxygen, one where the hydrogen is on the sulfur. Remember again, these little sticks that Gauss View is drawing here don't tell us anything about actual chemical bonds, so don't worry about the fact that yes, there are 2 little sticks drawn between this carbon and this sulfur. That's not a bond. It doesn't tell us that the bond is double. It doesn't tell us anything about the bond. It's just there for cartoon purposes. Now we have a problem. We have a troubling problem here. And our troubling problem is, look at this methyl group. Look at what happened to the methyl. There was a torsion Here, atom number 7 is lying in the plane with the sulfur. Here, atom number 7 has rotated out of plane. So we're going to have to be careful to recognize that as we look at the transition state for the proton number 3 moving from oxygen 2 to sulfur 8, our transition state is also going to involve a rotation of this carbon-carbon single bond. Now that's a thing that would actually happen in a real gas phase experiment. That's one of the things that would happen as you go from this stable conformation to this stable conformation. It's not going to make much chemical difference. The rotational barrier of this rotation is probably going to be below room temperature, so it's going to spin freely at room temperature. But when we do the calculation at 0 temperature, we have to account for this fact. So our next step is going to be to prepare a transition state optimization. And our transition state optimization file is going to have 3 geometries. Geometry number 1 is going to be the optimized geometry of the reactant. Geometry number 2 is going to be the optimized geometry of the product. Geometry number 3 is going to be a guess at the transition state geometry. Now, there are ways to build these input files inside of GaussView, but they're all terrible. At least I don't like them. So what I'm going to do is I'm going to build this input file by hand using Notepad. The way I'm going to do this is I'm going to start with the input file of the reactant, and then I'm going to add to it all the other things that I need. So I'm going to go to my Documents folder, and I'm going to open ohtautomer.gjf. Open it just in Notepad. So I have to look for all my apps that I could use to do things with. We're just going to use Notepad. It's nice and simple. Okay, now there's a couple things here. First step, we're going to save this as a different file. Save it as all files, and we're going to save it as tsopt1.gjf. Our first step, we're going to change the checkpoint file to be called tsopt1.chk. Second, this line tells us what we're doing. This tells us what kind of calculation we want to run. So we're going to change from optimization, the default, to opt something called QST3. It doesn't matter whether we use capital letters or small letters. We're going to delete this line that says geom equals connectivity. It just makes life more difficult. Now we're going to have to put 3 geometries in here. The first geometry is reactant geometry OH tautomer.log. So we need to have a blank line, the title, another blank line, this line that gives the charge and spin multiplicity. Charge is 0, the spin multiplicity is 1. These are all singlets. And now we're going to delete all of this. Delete it. We're going to paste in the optimized geometry from this calculation. So we're going to open this ohtautomer.log file. We're going to open it again in Notepad. And we're going to scroll way down to the end. Way down at the end is a section that says, here's the optimized parameters, which are really optimized bond lengths and bond angles and bond dihedral angles. And here is what we need. This section that says input orientation, center number, atomic type, and coordinates. This is the Cartesian coordinates of the optimized reactant geometry. There's 8 atoms, so we have 8 lines. We're going to copy those, and we're going to paste them as the next 8 lines in our input file. Now, for reasons, these 2 file formats are incompatible, so the first number that gives the index, we have to backspace through those. Get rid of that. Okay, once we've done that, we need the next geometry. So we need a blank line, a title that says optimized product geometry, SH tautomer. A reminder that two more blank lines, 0 and 1. Our molecule is still uncharged, it's still a singlet. And now we paste here the optimized product geometry. So we close OH-tautomer.log and we open SH-tautomer.log. We scroll down to the end again. We scroll back up. Get the optimized geometry and standard orientation. Copy these 8 lines and paste them in to our input file. Now hopefully you can see that these numbers are different from these numbers because the positions of the atoms in the product are different from the positions of the atom in the reactant. We again backspace through these initial lines. And now we need, for this QST3, the 3 means 3 geometry, so we need a third geometry. We're going to call that the initial guess transition state geometry generated from the product geometry. So I'm just going to copy and paste all of this product geometry again. And then later in Gauss view, I'm going to modify it. I need to modify it. I need to make changes to it. Couple of comments here. This line has to be blank. 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 Gaussian is very picky about the format of these files, and so you have to have all of these blank lines have to be there. The end of the file has to have one or more blank lines. All of these title lines have to be there. This checkpoint file has to have the right name. So I've got all of this, and I'm going to save it. Now, my next step is going to be to open this in Gauss view and make the modifications that I need to get a guess transition state. Modify this third geometry as needed. I'm going to go to File, Open, and I'm going to open the input files, and I'm going to open tsopt1.gjf. This file that I have here, I'm going to open it in Gauss view. And now what you can see is that this file has 3 different geometries. 1, 2, 3. 1, 2, 3. Note that the bonds are drawn differently this time. The little sticks, rather, are drawn differently this time, which is fine. We don't care about those little sticks at all. We should also view our labels and make sure that the atom numbers are always what they need to be. So the transferred hydrogen is number 3 here, number 3 there, and number 3 there. Now we're going to modify this last geometry, our initial guess at the transition state. We're going to make a couple modifications. Remember, our methyl group rotates when we go from the reactant to the product. That atom number 7 rotates down. So here we're going to use the dihedral angle tool to rotate it back up just a little bit, not all the way, just a little bit, to something intermediate between where it was in the reactant and where it was in the product. Just about like that. Okay. We're also going to move, and this is the really important part, move that proton from where it was in the product towards where you might expect it to be in a transition state. Well, in a transition state, the sulfur-hydrogen bond is going to be longer, and the carbon-sulfur-hydrogen angle is going to be smaller. There I was doing a rotate atom, which is not at all what I want. I want to fix atom number 1 so it doesn't go anywhere, and atom number 2 is fixed so it doesn't go anywhere. So when I change the bond angle, all that I'm doing is moving atom number 3. And we're going to start with it approximately in the middle. So that, I think, remember, ignore the little sticks. Ignore the little sticks. The little sticks don't tell us anything useful. All we're looking at is the positions of the atoms, and I think that the positions of the atoms are now a reasonable guess for the transition state. So now I'm going to save this. I'm going to save this file. I'm going to, just in case, I'm going to save it with a different name, TSOpt2. And I'm going to do one more thing. I'm going to reopen tsopt2.gjf in Notepad. And I'm going to make one change. This is going to slow things down. Add 2 commands here. calcfc no eigentest. The first one tells us I'm going to calculate vibrational frequencies, second derivatives of the energy. And the second one says if my initial guess transition state isn't perfectly a transition state, meaning it has some other small imaginary frequencies, not just one imaginary frequency, I'm not going to throw my hands in the air and cry about it. I'm just going to keep running the calculation because the initial guess geometry doesn't have to be perfect. Now you see Gauss View itself has made some modifications. It's modified the name of the checkpoint file, and it's added this geom equals connectivity stuff for each of these geometries. We can just ignore that. I don't care about that. But anyway, I'm going to save this. And now I'm going to run the calculation using Gaussian. tsopt2.gjf, tsopt2.bar. This will probably take a little while. This will probably take a couple of minutes. But once we get it to work, the good news is it didn't die immediately, and that means that the calculation is probably running correctly. I probably set up the input file correctly. Now I want to remind you that setting up these transition state optimization input files is really, really fraught with difficulty. There's lots of ways to have a little mistake or a little error or a little incompatibility make it not work out. So if you follow exactly what I did, you should be able to get it to work. But don't be surprised if your first try doesn't work. Don't be surprised if your second try doesn't work. Don't be surprised if there's a lot of little things you need to fix in these input files before you get the job to run. If you have a problem and you're not sure what's going on and you need to ask me, please copy and paste the input file into your email. It makes it a lot easier for me to debug when you send me exactly what you did. And look, the calculation is finished. We can't open log files in this version of Gauss View for reasons that I still don't understand, but we're just going to do the same format checkpoint, ts2.chk, ts2.fchk. Open. And look at that. Again, please don't worry about the little dotted lines, the little sticks. The fact that there's no little stick drawn here does not mean that there's no quote-unquote bond between the oxygen and the hydrogen. This is, in my view, a very reasonable initial guess transition state for this reaction. Now, in the second part of this video, we're going to go through some tools for how to confirm whether the transition state is reasonable and how to look at the corresponding potential energy surface. So we're going to exit out of this, and we're going to go on and get ready for part 2 of transition states.